Welcome back, everyone. So, today we're unpacking a really fascinating explainer on fractions. Now, I totally get it. For a lot of us, the moment whole numbers turn into fractions, math suddenly feels, well, kind of abstract and intimidating, right? But today, our goal is to completely transform those abstract fractions into everyday intuitive logic. We're going to look at the math of equal shares, break it down visually, and literally just make it make sense. Let's get into it.
Okay, let's dive into this. Let's actually start by looking at where the concept even comes from. Long before we were throwing around formal terms like numerator or denominator, ancient Indian mathematicians called a fraction bina in Sanskrit. And what does bina mean? It literally just means broken, part, or piece. When we reframe fractions this way, they honestly stop being scary math problems and start being exactly what they were invented for, just a super practical way to deal with broken pieces of whole things.
Here's our quick roadmap for this explainer. We'll start with 1, the art of equal sharing. Then move to 2, meet the fractional unit. 3, fractions greater than 1. 4, comparing equivalent fractions. And finally, wrap up with 5, ancient math and operations.
All right, section 1, the art of equal sharing. Let's ground this math in the absolute most relatable scenario possible, which is sharing food. Specifically, sharing rotis, or flatbread.
And this brilliantly illustrates the core concept. Look at the left side here. We have one single roti being shared equally between 2 children. Naturally, each kid gets half a roti, right? But over on the right, that exact same single roti is being shared equally among 4 children. Because more people are sharing the exact same amount of food, each individual piece just has to get smaller. They each get 1/4.
So that brings us to our absolute foundational takeaway for this whole explainer. When a whole number of things is shared equally among a certain number of people, well, fractions are simply the mathematical tool that tells us exactly how much each share is. They are literally just the language of equal distribution. Moving right along to section 2, meet the fractional unit. Because once we understand that fractions are really just shares, we need to meet the atomic building blocks of all fractions. But before I just show you, let's do a little Socratic questioning. Based on our roti example we just looked at, which fraction do you intuitively think is greater, 1/5 or 1/9? Take a second, really think about it. Usually our brains see that number 9, we automatically know 9 is bigger than 5, and we just assume, boom, 1/9 must be the bigger number.
But let's look at this fantastic realization from Arvin in the source text. He points out that exact common mistake, and then quickly corrects himself, saying, if one roti is shared among 5 children, each gets 1/5. If shared among 9 children, each gets 1/9. If I share with more people, I will get less. So 1/9 is actually smaller than 1/5. A larger denominator just means more people sitting at the table, which obviously means a much smaller slice of the pie for you. Now, these are all prime examples of what we call fractional units, or unit fractions. Whenever one whole unit is divided up into several equal parts, each single part is called a fractional unit, 1/2, 1/3, 1/4, going all the way down to 1/100th. Every single other fraction in existence is really just built by stacking these individual units together like Lego bricks. Let's move to section 3, fractions greater than 1, and see how this builds when we start combining those units to represent amounts that are actually larger than a single whole. Okay, so instead of one roti, imagine we now have 3 whole rotis, and we're sharing them equally among 4 children. How do we even do the math here? Well, if you divide each of the 3 rotis into 4 equal pieces, each child gets 1/4 from the first roti, 1/4 from the second, and 1/4 from the third. 3 times 1/4 simply gives us 3/4 of a roti per child. We're literally just adding up the fractional units. And this logic leads us perfectly into comparing improper fractions and mixed numbers. Let's take 3/2, or 3/2. That literally just means we have 3 of our 1/2 fractional units. Well, 2 of those halves clearly make a whole, with 1/2 left over. So the improper fraction 3/2 is exactly the same thing as the mixed number 1 and 1/2. It's just a slightly different way of grouping the exact same broken pieces. Which brings us to section 4. Comparing equivalent fractions. Now we're shifting our focus a bit to evaluation. How do we fairly compare fractions when the broken pieces are cut into totally different sizes? Now, what's really interesting about this slide is that completely different numbers can represent the exact same mathematical share. Look at this. 1/2 is exactly the same amount as 4/8. 4/6 is exactly 2/3. Even something messy looking like 17/51, yeah, that's actually just 1/3 in disguise.
We call these equivalent fractions. So, what happens if we need to compare two fractions that look absolutely nothing alike? Say 4/5 and 7/9. The text gives us this really great, logical, step-by-step method. Step 1, we find a common denominator, so we're actually comparing apples to apples. If we multiply 4/5 by 9/9, we get 36/45. Then, if we multiply 7/9 by 5/5, we get 35/45. Now the fractional unit is exactly the same for both, 1/45. And 36 of those units is clearly greater than 35 of those units. So, 4/5 wins the matchup. That underlying logic of finding a common base unit brings us to our final section, ancient math and operations. And honestly, the deep historical roots of the math we're learning here are just mind-blowing. The explainer gives us this wonderful pinch of history right here. Did you know ancient Indian mathematicians were writing fractions in a way that looks incredibly familiar to us today? The Bakshali manuscript, which dates all the way back to around 300 CE, shows numbers written one over the other, just without the horizontal dividing line we use now. And by 628 CE, a mathematician named Brahmagupta laid out the concrete rules for adding and subtracting them.
So the crucial point is Brahmagupta's method, which is literally the exact same method we use 1400 years later. His rule was beautifully simple. When you're adding or subtracting fractions, you first convert them into equivalent fractions that share the exact same fractional unit, the same denominator. Once the pieces are all the exact same size, you simply add or subtract the number of pieces. You literally just do the math on the numerators. The explainer uses this cool rectangular strip model to visually anchor this idea. If we want to add 4/7 and 6/7, we don't have to do anything complicated at all because the fractional unit, 1/7, is already identical. We just look at a strip divided into 7 parts, we take 4 shaded parts, we add 6 more shaded parts of the exact same size, and boom, we get 10 shaded parts. 10/7, which is 1 whole and 3/7. It's seriously just counting pieces. Okay, so let's put this into practice. I'm going to challenge you with a real problem from the chapter right now. Jaya's school is 7/10 of a kilometer away from her home. She takes an auto for 1/2 of a kilometer, and then she walks the rest of the way. The question is, how far does she walk? Let's apply Brahmagupta's ancient method here. So to find her walking distance, we obviously need to subtract the auto distance from the total distance. That's 7/10 minus 1/2. But wait, first we absolutely need a common fractional unit, right? We know 1/2 is totally equivalent to 5/10. So now the problem is just 7/10 minus 5/10. 7 pieces minus 5 pieces leaves us with exactly 2 pieces, 2/10. And if we quickly reduce that down to its lowest terms, we get our final answer. Jaya walks 1/5 of a kilometer. And honestly, you guys, that is the true beauty of this math. By breaking things down into equal shares, finding that common fractional unit, and just making sure we're always comparing the same size pieces, fractions become virtually effortless. So I'll leave you with this thought to chew on. If Bina really just means broken piece, and all fraction problems are solved simply by finding a common denominator to understand those pieces, what other complex, broken problems in your life could be solved by just zooming out, finding common ground, and comparing apples to apples? Thanks so much for learning with me today. See you next time.